Hello, everyone. Welcome to the third talk of the session. Please put your hands together for Emily, and she's going to talk about AST and me.
Hello, everyone. This is my fourth PyCon, so I'm feeling very comfortable, kind of like an old timer at PyCon. I've gotten to meet a lot of great friends here. This is my first time speaking at PyCon, and it's always been a dream of mine. And I've finally gotten here, and I'm doing it. So thank you all for having me. I'm very, very happy to be here. So a little bit about me first. My name's Emily Morehouse. I am the director of engineering at a company called Cuddlesoft. We're a digital product development company where I get to work on anything and everything from CI/CD pipelines, system architecture, web and mobile development, UX, and IoT. But don't tell anybody else, Python is still my favorite language. So here's a little bit of what we're going to cover in this talk. We're going to walk through the life cycle of a piece of Python code from a very 10,000-foot view perspective of this. We're going to detail how you can actually interact with your code at various stages of this pipeline. And then we're going to talk a little bit about the current optimizations in the Python compilation process. And then we're going to talk about some practical applications of using ASTs to build really cool tools. So the question always is, should you really care about language internals? And my answer is yes. Yes, you should. So we're going to take a quick peek under the hood of Python. So we're going to start our journey from source code to execution in order to build an understanding of the broad steps that it takes to compile a piece of Python code. So the first question is Python compiled or interpreted? Yes, and that is exactly the right answer. It's both. So we have our compiler that generates bytecode, and then our interpreter that makes sense of that bytecode in order to execute your code. And so one of the ways in which Python is considered to be a dynamic language is that the same exact bytecode doesn't necessarily always have the same exact outcome. So let's zoom in a little bit to see a little bit more of this process. So, as most of us do, we start with our source code. Our source code then gets tokenized and parsed into what's called a parse tree. Now, parse trees are a little bit more detailed than what we actually want to deal with. So we could transform that parse tree into an abstract syntax tree. We do then another transformation into what's called a control flow graph, or a CFG, which is essentially a directed graph that helps model the execution flow of your program. We then take that to emit our bytecode, and then the CPython virtual machine takes that bytecode and executes it to get our final output. Now, this is quite the intricate process with a lot of steps to it. So we're going to focus down on a few key parts of this process, namely our source code, the abstract syntax tree, and our bytecode. So what actually is an abstract syntax tree? Simply, it's a structural representation of your code in a tree format, where every node represents a different type of language construct, such as an expression, a statement, a variable, a literal, anything like that. So what exactly is a tree? To make sure that we're all on the same page here. Because this is a tree, and this is also a tree. So when we start with a tree, they have one root node, the top node. Nodes can branch off down to other nodes, but each node except for the root node has a single unique parent. So when we read this, we start at the top node and work our way as far down the first branch as we can before we start on the next side, performing a depth-first traversal. So let's look at the difference between our two types of trees that we've talked about. So we have a very simple piece of code. We're going to start with 1 plus 2 in parentheses times 3. And so on the left here, we have a parse tree for this code, which is essentially going to be a one-to-one mapping of your Python code into a tree form. You can see that we have all of our expressions, our terms, our factors are modeled here in this tree. But it's actually a fairly complex tree for such simple piece of code. So what we can do is we can kind of remove all of the syntactical expressions that we need to define the code and simplify it into an AST. So this is the AST for the same exact piece of code. We've left behind all of these syntactical specifics so that we can actually focus on the underlying semantics and the true meaning of our code. So it is important to note that there's information that you lose when going from your parse tree or your CST into an AST. And that's very much on purpose. A CST has all of the information from your source code, including things like comments, whereas an AST is sort of stripped down and simplified. So ASTs are simpler and easier to work with, but they might not have all of the information that you need to interact with your tree. All right, so now that we have a really good example of what an AST is, what the overview of the compilation process is, let's dig in and see how we can interact with this in our terminals. So we've got some primary tools. There are a few built-in libraries in the Python standard library. One of them is the AST module, which allows you to build ASTs and compile different trees and nodes based on a piece of code. And it lets you introspect those ASTs as well. And then we have the dis module, which allows us to disassemble pieces of bytecode and make them a little bit more readable and easy to work with. There are also some really neat secondary libraries that have been written. There's one called Aster, there's one called Meta, and CodeGen. So if you have any interest in messing around with ASTs or injecting things into ASTs or comparing them, these libraries are really, really, really helpful. So let's dig in. First, we're just going to import the built-in modules that I just mentioned. And then we're going to start with a very simple piece of code, simply a print statement that takes in a string as an argument. So from here, we can use our AST module to generate our nodes. So we specify the source when we're working with this, as well as the mode that we want to process our code in. So it's actually really important for us to use exec here as opposed to eval, because it allows us to run any sort of Python code that we choose, whereas eval only allows us to run expressions. So from here, what actually do we get from this ast.parse? Since we did use exec, we get back a module. And we can dump this module, but this isn't really very readable. So if we dig into this a little bit, we can see that we have a function with an ID print. We have an argument that's a string that's getting passed in. We don't have any keyword arguments. But this isn't really very easy to work with. So let's kind of keep pushing forward. We can take this AST and compile it. And all you have to do is simply call compiled. We're going to store this into a variable so that we can kind of poke at it a little bit more. So compiled actually becomes something called a code object. And if we poke a little further, we can see that we've got a bunch of methods and variables that are defined here. A lot of this is going to be stuff that is needed by the interpreter in order to run this code. But there are some very important parts of code objects that we can use. So what is a code object? Code objects are simply immutable data structures that are used as an internal representation of your Python code that is generated by the Python interpreter. They store a lot of necessary information that you need to run the code. There are a lot of different parts to our code object. Most of them are only meaningful to the bytecode interpreter, but there are a few really interesting parts that we can dig into. So one of them is co-name. All of these are kind of prefaced by co_. And this is going to be, if it's a function, it's going to be the name of the function. For our class, it would be the class's name. In these examples, we're using modules, so we can't actually tell compile what we want this to be called. So it's just going to be called module. There is also co-var names, which is a tuple that contains all the names of your local variables, including your arguments. You have co-stack size, which is the maximum stack size that is it's computed statically by the compiler. You have constants that you can look at, which is another tuple that contains all of the code literals. And then co-arg count, which is also positional arguments where we can receive information, and then also the default values that are associated with this. And our most important part for us in this talk is our code, which is a string representing the sequence of bytecode instructions. So let's take a look at what that looks like. So we've peeked inside of our code object and seen a bunch of different things. And this definitely looks like something that a computer would understand, but not necessarily something that a human could understand right off the bat. But we can indeed take this compiled code and call exec, and it will run the code that we have specified. So let's go back and take a closer look at that bytecode. So what we can do is force our interpreter to show us the bytecode in a way that's a little bit more legible for humans to read. Somewhere along the lines, our compiler makes sense of these bytes, but it would take a lot of time for us to go through. There's actually a giant switch statement that handles all of these opcodes. But again, it's super readable for us as humans, right? I can't tell you what exactly the opcodes for 100 and 101, et cetera, do. So we can now call up our handy dis module and then get this to help us out. So we have a little bit more clear depiction of what's going on here, right? So we see that we are loading up the function print, we're loading up the constant that we have passed to it, we're actually calling it, and then returning. There's also a built-in helper function that you can use to print out a bunch of the useful information here. So as I mentioned earlier, you can see that our name is module, our file name is just string because that's where we specified our source. We don't have any arguments or keyword arguments. We see that our stack size is 2, and we have a constant that is may the force be with you. So now we know what all this looks like in bytecode form and some machine instructions, but what does all of this look like in tree form? So here's our AST as well as our disassembled bytecode for our print statement side by side. So this is actually pretty readable at this point. We see that there's a single statement, so we don't need any sort of nesting in our AST. We'll call load name for our print statement, load const for our string that we passed in. This is a little bit more simplified since we directly pass this into dis as an expression. So then we call load const for the string we passed in and simply execute, right? So this is simple enough. But as we continue to add code, even just a simple if statement, or say a variable declaration, we say that our examples get progressively more and more complex. But our ASTs still help us visualize the path that our code takes. However, a caveat to this all is that what we wind up with in our AST or bytecode is not necessarily going to match our source code one-to-one. There are certain shortcuts or optimizations that our compiler makes when creating our bytecode. So let's take a look at what sorts of optimizations actually can affect our bytecode. So Python's compiler is purposefully relatively simple. Or at least as simple as it can be. So the best way to optimize Python is actually to replace the implementation for another interpreter, like PyPy, Jython, Cython, IronPython, Stackless Python, MicroPython. The list goes on and on and on because there are so many different uses for Python and people want to optimize them for those usage, or they want to try to speed them up, right? So Python, the language itself, is completely independent of the implementation that is used to bring our language to life. We're also going to talk about the people optimizer, as well as a few other optimizations besides constant, or there are actually very few optimizations outside of constant folding that we see in the AST, but we're going to dive into that a little bit more in a second. So people optimizations. The way that I really like to think about people optimizations is kind of looking around without moving your head. It's really using that peripheral vision to see what is directly around you and what you can use from that information. So a really easy, simple demonstration of this is taking something like x equals 1 and y equals x plus 2. So anybody who's gone through a fairly beginner algebra class can say, oh, okay, if x equals 1, then I can say y equals 1 plus 2. And that's exactly what the people optimizer will do. It gets a little bit more tricky once you actually are implementing this in a full language, but that's a good way to think about the concept. Another thing that the people optimizer will do is it will actually fix any sort of double negatives that you write in your code. So if you write not A, not in B, the compiler goes, oh, okay, no, hold on a second. I know what you really meant. I can simplify this down to just A and B. And so you can see when we run the disassembler on this code that our output is exactly the same for these two different expressions. So that's just one way that your source code might not one-to-one match what you expect to see in your AST. All right, so constant folding. Evaluating constant expressions at compile time. So constant folding is just the process of recognizing these expressions and computing them at compile time as opposed to at runtime. So terms in these constant expressions are typically simple literals, such as the integer literal 2, but they also might be variables whose values are known at compile time. So here's a quick example of that. If you have a equals 2 times 3, that can get simplified down into just a equals 6. Actually, let me go back real quick. So not all languages do this, and it doesn't happen all the time, but this is a way that it can change what your bytecode looks like. All right, so how the AST actually affects your code. So we now know that bytecode is created using an AST, and all of our bytecode is actually stored in PyC files. Before Python, well, from 3.2 and previous, we also had PyO files. After 3.2, all of these files have been organized into like a PyCast directory. So if you ever see that hanging around and you try to look at those files and you realize that you cannot read them, that's bytecode. Let's see. So since we have this bytecode that gets generated at compile time, one way that we can improve the speed of running our code is to store all of our bytecode into files so that we're not regenerating that code every single time we build a project, right? So Python uses something called a magic number in order to determine whether or not it actually needs to regenerate our bytecode if something has changed in those files. But at this point, you're really only going to get very micro speedups from looking at these small differences and optimizations that the AST actually does. Like I said, to get major speedups, you're really going to have to actually change out the Python implementation that you're using. All right, so some example applications and projects that I really enjoy using ASTs. Code generators are really, really neat. A fun fact that I got to learn along my journey is that there is actually a lot of the Python compiler itself that is generated code. But in Python, there are neat projects. So there's one called Hypothesis that is a test generation library where you can actually give it your code and maybe give it a couple of like baseline tests, and it will actually run through your code and will generate tests for you in hopes to kind of cover cases that you didn't necessarily expect your code to go down. So it helps you kind of identify those edge cases in your code and actually write tests for them. There's an older library called Cog. I think it was last tested on 3.6. But it allows you to essentially take a file and write little templates in there to generate different parts of your code or just text in general. Like I mentioned, there are a lot of alternative interpreters. You can actually transpile or use kind of alternative compilations. So say you're going from Python to JavaScript or Java. So there's a really neat part of the PyView project called VOC that allows you to kind of compile your code from Python into different native code. There's one called Transcript for Python to JavaScript. And there's a lot of ways to do code transformations. So ASTs really show up in a lot of different tools that many of us probably already use. So stuff like Jinja, it's a templating engine. And under the hood, Jinja actually uses an AST in order to parse your code from the HTML and add in all of your variables and kind of spit it out at the end as a full HTML template. Some other example projects, there's some really neat stuff that you can do with code analysis. So there's a project from Python Security, it's called PyT, that is able to parse your code and analyze it to see if you have any sort of security vulnerabilities. And things that I hope that all of us are either use or will be using soon. Code linting. There's many code linters that are built into your editors, or that you run on your code before you push it, or maybe it gets run in continuous integration. Those all rely on ASTs. Code formatters, there's a few of these. Yet another Python formatter that's owned by Google. There's Black, that is a newer Python formatter. And Prettier, which is a JavaScript formatter, if you're in that world. And then code transformations. These are the things where it starts to get really interesting. So there are tools like PostCSS or Babel, or even just migrating your code from Python 2 to 3, where you can take existing source code, figure out how it needs to be altered, and then spit out code that works in different environments. So something like Babel will take really advanced future functionality in JavaScript and compile it down so that it can actually be run in all browsers across the board. And tools like React Native, which is kind of along the lines of what PyB does, where you can write native mobile applications in a language like Python or JavaScript that's going to be a lot easier to work with. And you can have cross-platform applications where you have a single code base, but they're actually generated down into native code. And so we've seen that maybe you can speed up your code. I don't really think that looking at the AST is going to get you very far in that. In certain ways, knowing how the AST works can help you debug errors or oddities. There are certain cases where if you're trying to get 100% code coverage, or you're not sure why a certain piece of your code is not showing up as being tested, there are certain ways that the compiler will optimize pieces of your code out because you don't really need them. There are also ways that you can get in there and change the Python grammar. If you're really excited about a new language feature, you have an idea for something that you like want to mess around with for a new syntax in Python, you can get in there and change that up. And then one of the things that I really enjoy is called round tripping. It seems to be the thing that a lot of people get excited about. So with round tripping, you can essentially take the AST from your source code before you make any changes to it, and then the AST from after you've made changes to your source code, and compare the two and see how they differ. So this is actually really beneficial when you're doing something like code formatting, where you can make sure that the underlying syntax of your code matches before and after you've made the changes. So I hope that this talk kind of gives you a really good idea of how Python is compiled, what an AST is, and how you can use the AST to build really awesome tools. At this point, this was scheduled to be a shorter talk, so I'm going to end a little bit early. I'm not going to take questions, but if anybody wants to come up afterwards and talk about anything from this talk, I'm available. Thank you.